think about the physical space right now, just
Mhm.
between you and whatever device you're using to listen to this.
Right.
We naturally default to viewing that space as just um, a passive, empty stage, just a place where the events of the universe happen to play out.
Yeah, that's the standard intuition.
But what if that assumption is just completely backward? What if understanding the internal mechanics of, like, a single microscopic proton could actually decode the largest, most impenetrable mystery of the entire cosmos?
Well, framing the vacuum as just a static theater is basically a classical physics
A
hangover.
hangover, yeah.
Exactly. I mean, the bleeding edge of modern theoretical physics suggests the stage itself is actually alive. It's constantly interacting with the actors on it and generating the very forces that dictate how the universe evolves.
And today's deep dive is really centered on tearing down that classical hangover for you. We're examining the work of physicist Boris Krieger through two incredibly dense but absolutely groundbreaking papers.
Really fascinating stuff, yeah.
And our mission here is to trace the math from the absolute largest scale, so dark energy and the cosmological constant, all the way down to quantum chromodynamics.
Which is just the theory describing how quarks behave.
Exactly. Now, to set the parameters, the first paper we are looking at is titled The Cosmological Constant as a QCD Observable, Derivation, Nonlinear Screening, and Falsification.
Which is a title that just lays all its cards on the table.
Yeah.
I mean, it promises to take something we observe on a cosmic scale and derive it strictly from the behavior of the strong nuclear force.
Yeah, no holding back there. And the second paper, it acts as the crucial foundation for that derivation. It's titled Density Dependence of QCD Vacuum Energy from Nucleon Sigma Terms.
Right.
And Krieger's core thesis across both of these texts is that the vast vacuum of intergalactic space and the microscopic math governing quantum particles are actually the exact same physical problem.
Right. They aren't separate domains. To tackle the whole universe, we really have to start by redefining what the vacuum actually is when we, zoom all the way in.
Okay, so take us in, zooming all the way in, what is the vacuum?
Well, because we are dealing with quantum chromodynamics, so QCD, we have to look at empty space through the lens of the strong force.
Right.
The QCD vacuum isn't empty. It's actually just the mere presence of a piece of matter fundamentally changes the energy value of the empty space surrounding it.
Which is wild, and Krieger leans on a very specific, unambiguous measurement to demonstrate this shift, doesn't he?
He does. He uses the strangeness sigma term.
Mm.
So in particle physics, a sigma term essentially measures how much the mass of a nucleon changes in response to the quarks in the vacuum.
Okay.
And the strangeness sigma term is measured at approximately 40 megaelectron volts, or MeV. Now, the reason this number is so critical, so mind-blowing, is found when you look at the actual composition of a proton.
Right, because a proton contains two up quarks and one down quark.
Exactly.
So it has zero strange valence quarks.
Zero. The proton itself has absolutely no strange quarks in its permanent architecture.
Wow.
Yet, experimental physics definitively shows the proton is interacting with the strange quark, condensate bubbling in the vacuum around it.
That's crazy.
It is. The proton is mathematically communicating with strange quarks that belong to the empty space, not to the proton itself.
I picture this kind of like dropping a really heavy bowling ball onto a tightly woven trampoline.
Okay, I like that.
Right. So the bowling ball is made of, say, dense resin, and the trampoline is woven nylon. They are completely different materials.
Right.
But the moment that ball rests on the fabric, its mass stretches the nylon. It pulls the fibers tighter and changes the tension of the entire surface radiating outward.
That's a great way to think about it.
The ball and the trampoline are intimately interacting just because the mass is occupying that space,
Yeah.
even though they aren't made of the same stuff.
That mechanical analogy works perfectly because the strangeness sigma term is the literal mathematical measurement of that changing tension.
Wow.
Because a proton lacks any strange quarks of its own, this provides model-independent proof that the background fabric of the universe is bending and responding to the mass. It's not just a quirk of the math.
It's an active physical response.
Exactly. And Krieger scales this up. He calculates that at a finite baryon density, this vacuum energy shift actually constitutes roughly 10% of the total energy density.
10%.
Yeah, it represents a massive chunk of reality's energy budget.
So if every single proton in the universe is shifting the vacuum locally, those tiny local stretches, they have to compound, right?
Oh, they definitely compound.
And when we zoom out from a single proton and look at the macro structure of the universe, we hit what's known as the cosmological constant problem.
Yeah, which physics often calls the worst prediction in the history of science.
The absolute worst. Give us the scale of how bad this prediction is.
The discrepancy is legendary. So the cosmological constant, denoted by lambda, is the vacuum energy density that's actively driving the accelerated expansion of the universe.
Right.
But when physicists attempt to calculate this value using Planck scale quantum gravity, the result overshoots observed reality by a factor of 10 to the power of 120.
10 with 120 zeros after it.
Yes, it is a number so absurdly wrong it just stops being mathematically useful.
But Krieger's approach, he actually ignores that 120 zero problem entirely, right? He targets a second layer of the discrepancy.
He does. He focuses on the QCD chiral condensate estimate. So if you try to calculate the vacuum energy of the universe using only the baseline QCD chiral condensate we just described.
Well, the Planck scale stuff.
Right. You still overshoot the observed cosmological constant by a factor of 10 to the power of 42. And Krieger's first paper is essentially an active mathematical assault on that 42 order of magnitude gap.
But I mean, bridging a gap of 10 to the 22, that requires a fundamental reevaluation of the mechanics. It's not just a rounding error you can tweak.
Oh, definitely not. So Krieger derives a closed-form expression for the cosmological constant, which he labels lambda 0, by introducing two massive suppression factors, things that traditional estimates completely ignore.
Okay, what's the first one?
The first mechanism is confinement. In QCD, quarks are confined. They cannot exist freely in isolation.
Right, you can't just have a lone quark wandering around.
Exactly. Their color fields are locked inside hadrons, like protons and neutrons. So because the source of the vacuum energy is intimately tied to these tightly bound color fields, the vast majority of that potential gravitational energy is shielded.
Shielded.
It is. And when Krieger applies the mathematics of both that confinement shielding and this geometric cycling feedback loop, the 10 to the 42 error just vanishes.
It just disappears.
Pretty much. He derives a coupling constant, alpha, which he calculates to be exactly 0.005.
Okay.
Running that alpha through his expression with those suppression factors yields a calculated cosmological constant of about 3.0 times 10 to the negative 52 inverse square meters.
And what do our telescopes actually see?
Telescopes observe the actual real-world value at 1.1 times 10 to the negative 52.
Wow.
Yeah. He takes a math problem that was fundamentally wrong by 42 orders of magnitude, and he reduces the error down to a factor of roughly just 2.8.
Just a 2.8 difference. That means this theoretical derivation, which is built entirely on the strong force behavior of subatomic quarks, suddenly lands in the exact same neighborhood as the size of the observable universe.
That's a staggering convergence of scales.
It really is. But before we just, accept that 2.8 factor as the total victory, I need to throw a reality check at this model.
Lay it on me.
If the vacuum energy is intimately tied to the density of matter, right, well, we have a profound density of matter in our immediate solar system.
We do. The sun is pretty massive.
Right, the mass of the sun is staggering. So if this local vacuum shift is real, wouldn't the resulting gravitational vacuum energy pull the Earth into the sun way faster than standard orbital mechanics predict? Why aren't we burning up?
That is the exact right question to ask. Any theory modifying gravity or vacuum energy absolutely has to survive the solar system test.
And does it?
Krieger runs the numbers for our local interplanetary medium. Based on his model, this localized vacuum source produces an additional gravitational acceleration equivalent to 10 to the negative 30 times the standard solar field at a distance of 1 astronomical unit.
Wait, 10 to the negative 30? That's vanishingly small?
It is essentially ghost. We use lunar laser arranging to measure gravity in our local pocket, basically bouncing lasers off lunar mirrors to track orbits down to the millimeter.
Right, highly precise.
Extremely. But lunar laser ranging operates roughly 25 orders of magnitude above the effect Krieger is describing.
So we couldn't even see it if we tried.
Exactly. The phenomenon is entirely cloaked by standard classical gravity on the scale of a star system. It only crests into a visible, measurable 1% enhancement when you compound it over massive galactic scales.
Where the distances between stars are vast enough for those tiny microscopic modifications to finally accumulate.
Yes, the sheer volume of empty space allows it to add up.
Okay, well, this raises a massive implication.
Hmm.
If the math works for the cosmic expansion at galactic scales, and it works for quarks,
Yeah.
there's another cosmic mystery sitting right in that exact same crosshair.
Dark matter.
Dark matter.
Right.
Because I dug into that coupling factor alpha, the 0.005 number. The notes in the paper point out it is mathematically equivalent to the scalar quark content of the nucleon.
Yes. And the synthesis between Krieger's two papers really crystallizes around that specific equivalent.
It's a huge deal.
It is, because the scalar quark content is the central mathematical value governing spin-independent WIMP nucleon cross-sections.
Okay, let's break down that terminology for the listener. WIMPs, or weakly interacting massive particles, they are a primary candidate for what dark matter actually is.
Right.
And when astrophysicists bury those massive liquid xenon detectors deep underground, they're essentially trying to measure cross-sections.
Yes, and think of a cross-section like the size of a bullseye on a dartboard.
Okay.
It's not a physical slice of an object. It is a probability measurement. The larger the cross-section, the higher the probability that a ghost-like dark matter particle will bump into a normal nucleon in a way our instruments can actually detect.
Right. A bigger bullseye means more hits.
Exactly. And the scalar quark content is the numerical parameter that dictates the exact size of that probability bullseye.
So discovering that alpha is equivalent to the scalar quark content, it's kind of like realizing the exact mathematical formula dictating how tightly a guitar string is pulled, also perfectly predicts the kinetic force of ocean waves crashing on a beach.
That's a wild connection, but yeah, mathematically, it holds up.
It proves two seemingly completely unrelated phenomena. So the dark energy pushing the universe apart and the dark matter pulling galaxies together, they're running on the exact same hidden engine.
It unites the cosmic dark energy budget directly with the microscopic sensitivity of dark matter direct detection experiments. The identical physical quantity drives two completely distinct contexts.
Incredible.
But there's a catch. The raw theoretical alpha of 0.005 derived from the math actually differs slightly from what we would observe across different cosmic epochs.
Oh, really?
Yeah, which requires Krieger to introduce something called nonlinear screening.
Because the universe is expanding, right? So the relationship between matter and the vacuum has to be inherently dynamic. It's not static.
Exactly. And to prove this, Krieger built an n-body particle mesh simulation to literally map this dynamic relationship over time.
An n-body simulation.
Yes.
Yeah.
This involves programming a digital cube of space, roughly 256 megaparsecs across, populating it with 2.1 million particles to represent mass, and mathematically evolving that entire box from the early universe at a redshift of 49 all the way forward to the present day.
So basically, building a digital universe allows you to just sit back and watch the geometry of empty space change over billions of years.
That's exactly what he did. The simulation visually tracks the evolution of cosmic voids, so those massive empty regions between galaxy clusters.
Right.
In the early universe, these voids accounted for roughly 50% of the total volume. But today, because of cosmic expansion, those voids have grown to dominate 72% of the universe.
72% is just empty void.
Yep. And because Krieger's vacuum modification is strictly tethered to the presence of matter, the expanding voids physically squeeze the effect.
Wait, the voids squeeze the energy.
Yes. The vacuum energy modification gets pushed out of the growing empty spaces and becomes concentrated, or confined, into the shrinking, overdense regions where the galaxies actually reside.
So the effect is geometrically amplified in the places where matter clumps together, simply because the expanding empty space is shoving it out.
Precisely. The simulation measures this spatial confinement as a screening factor of about 3.9. And this nonlinear geometric screening perfectly bridges the gap between the raw theoretical derivation of alpha and the slightly altered values required to explain the observed universe today.
The elegance of connecting the quantum scale to dark matter, all through a simulated digital cosmos, is just fascinating. But, you know, elegance doesn't always equal truth.
No, it definitely doesn't.
Theories uniting everything under one umbrella, they often fall apart the second you force them into a laboratory. Falsifiability is the mechanism that separates actual physics from just pretty philosophy.
100%.
So where are the weak points in this model? What could shatter the math?
Well, Krieger is very upfront about this. He details the experimental tensions his theory relies on, primarily focusing on the foundational measurement of the pion nucleon sigma term.
Okay, so a different sigma term than the strangeness one from earlier.
Right. This value dictates how light quarks interact with the nucleon, serving as the absolute bedrock for the rest of his calculations. But currently, the global physics community cannot agree on this number.
Really? How far off are they?
There is a volatile 40% spread in the measurements right now.
40%. That's huge.
Yeah.
If the base measurement is unstable, everything built on top of it wobbles.
Absolutely. Phenomenological measurements, which involve observing exotic structures like pionic atoms, they yield a value of roughly 59.1 MeV.
Okay.
But in contrast, lattice QCD, which utilizes massive supercomputers to simulate the strong force interactions on a discrete grid of space and time, produces results ranging anywhere from 41 to 55 MeV.
Oh, wow.
Yeah, and Krieger openly states this discrepancy is the dominant source of uncertainty in his entire framework.
But aside from just uncertainty, he also provides a very rigid list of ways his framework can be definitively broken, right? He draws some hard lines in the sand.
Very hard lines.
And one of the most severe lines involves the speed of gravitational waves.
Right. Krieger's model dictates that the propagation speed of gravitational waves, denoted as cograv, must exactly equal the speed of light in a vacuum, c.
Wait, exactly equal.
Exactly. If future gravitational wave observatories detect a deviation between cograv and c greater than 1 part in 10 to the 15, his model is instantly falsified. It's dead.
Why is that specific speed so mechanically vital to his theory?
Because if gravitational waves do not travel at the speed of light, it implies the graviton has mass, or that spacetime has some dispersive property, and that would require a heavily modified theory of general relativity.
Ah, gee.
Krieger's derivation relies strictly on standard general relativity, or the cosmological constant arises purely from the stress-energy tensor of the QCD vacuum. If gravity itself propagates differently, it completely breaks the geometric foundation, linking his vacuum energy derivation to the curvature of spacetime. The whole coupling fails.
Coupling just snaps.
Yep.
And he applies that same strict threshold to the supercomputer simulations we mentioned earlier too, doesn't he?
He does. He utilizes a technique called naive dimensional analysis, or NDA.
NDA. Yeah.
NDA is basically a tool physicists use to estimate the magnitude of complex terms in an effective field theory, simply by analyzing their physical dimensions and the natural energy scales involved.
Sort of like a highly educated mathematical guess.
Exactly. And Krieger uses NDA to estimate the curvature response coefficient, known as C1, which dictates exactly how the chiral condensate responds to the bending of spacetime.
Which is the cycling feedback loop we discussed earlier.
Yeah.
The governor.
Yes, exactly. Krieger states that if future, more advanced lattice QCD simulations generate a curvature response coefficient that is inconsistent with his naive dimensional analysis estimate beyond an order of magnitude accuracy, the theory collapses entirely.
He doesn't leave much wiggle room.
No, and he even provides a precise benchmark observable, R alpha at mu b. And this is specifically designed for lattice QCD computations, calculating finite baryon chemical potential. He is literally handing the scientific community the exact mathematical target required to test his equations using current Taylor expansion techniques.
He builds the universe in a box and then hands you the hammer to try and smash it.
That's the scientific method at its best.
It really is. And, this whole deep dive into sigma terms, cross-sections, and chiral condensates, it forces a radical shift in how we perceive our daily reality.
He completely flips the script.
It does. You are not a passive observer moving through an empty void. The matter composing your body right now, the nucleons in your bones, in your nervous system, is actively conversing with the quantum vacuum.
Simply by taking up space, your physical mass stretches the fundamental energy fabric of the universe.
And that active continuous dialogue between mass and empty space that really anchors Krieger's entire premise.
It does. But, tracing the logical trajectory of that nonlinear screening simulation we discussed earlier, it introduces a pretty stark reality about the deep future of the cosmos.
How so?
Well, Krieger notes that as the universe ages, the physical volume of those cosmic voids inevitably grows. We went from 50% to 72% already.
Right.
This progressively forces the vacuum modification into smaller and smaller pockets of matter. The voids squeeze the effect tighter and tighter as the universe expands,
Okay.
which forces us to ask what happens at the absolute end of that timeline.
Oh, wow.
Right. As the universe continues to accelerate outward forever and matter drifts infinitely far apart, Does the fundamental structure of the quantum vacuum change?
Because there's no matter left to interact with.
Exactly. In a trillion years, when the galaxies have entirely dispersed and the local pockets of matter dissolve, the vacuum loses its conversational partner.
That is haunting.
If the vacuum's energy shift intrinsically requires matter to react to, what happens when the matter is gone? Does the empty space of the deep future simply forget how to have energy?